Okay. Hi guys. Sorry I'm not here today, but you're lucky in that now you get a video with me instead. Woohoo. So, okay. This video, it's going to be review of some calculus stuff, single variable calculus stuff, which will come in handy for the homework that I'm going to assign right after you watch this video. Um, So let me first do a little bit of pre-calculus review. You guys ought to remember that cos squared of some angle plus sine squared of some angle equals 1. And if you don't know that, then you should probably leave now. But otherwise, you can derive a couple other trig identities out of this. Like if I were to divide everything by cos squared, then the first term would turn into a 1, and then the second term would turn into a tan squared, because sine over cos is tan, and then the third term would turn into 1 over cos squared, which would be secant squared. Okay, so there's another trig identity, and then a third trig identity. If I were to take the first one and divide everything by sine squared instead, then cos squared over sine squared would be secant squared. No, cotangent squared, sorry. And then sine squared over sine squared would be 1. And then 1 over sine squared would be cosecant squared. So these three things right here, 1, 2, 3, these are three major trig identities that come in quite handy, especially for integration. And so here's, we'll do two examples directly related to some homework problems. So example 1, we'll find the integral from 0 to 1 of 1 over 2x squared plus 2 dx. Okay, so first thing, let me factor out a half. So I'll just throw that all in front of the entire integral. So 0 to 1 of 1 over x squared plus 1 dx. Okay, and maybe, I don't know how much these were drilled into you last year, or I don't even know if AB covered this stuff. I'm not sure where the split is anymore and what's covered in AB versus BC. But you might already have memorized what the integral of 1 over 1 plus x squared is. And if you do, great, no problem, just do it. And this one comes up enough where it might be worth memorizing it. But if you don't have it memorized, you can use a trig substitution to help. Notice x squared plus 1 looks a lot like this. 1 plus x squared is a lot like 1 plus tan squared. Now you can do it with 1 plus cotan squared, but tan is going to be easier to work with than cotan. So if I do a u substitution right here, or sorry, a trig substitution, not a u substitution. So we're going to let x equal tan theta. So x squared plus 1 is really going to be secant squared. Since we're switching stuff around, I'm going to have to figure out what dx is in terms of d theta. So dx, if I take the derivative here, dx d theta would be secant squared. So I'll write it like this. Dx d theta would be secant squared theta if you remember the derivative of tangent. And so then dx is going to be secant squared theta, and then if I bring that d theta over, there it is. So this is the trig substitution I want to use on this problem. So then this turns into 1/2, and I'm going to leave the limits of integration off for now. So that's going to turn into 1 over secant squared theta, and then dx turns into secant squared theta d theta. So secant squared theta d theta. The secant squareds will cancel, which is nice and convenient. And now I'm working in terms of theta, not x. So you can plug in the theta values here, Or you can just, if you're going to switch everything back to x at the end anyway, then you can also just say this will be whatever theta is when x was 0 to whatever theta is when x is 1. And then at the end, when we switch back to x's, you can just switch that back to 0 and 1. So what I've got right now is 1/2 the integral from theta of 0 to theta of 1. And let's see, and it's just d theta right here. So that's going to turn into 1/2 theta from theta whenever we plug in 0 to theta whenever we plug in 1. And then if I switch back, I've got 1/2 theta. So we have to do another thing here. Theta is going to be tan inverse of x. So it's 1/2 tan inverse x. And now that I'm back in x's, I'm just going from 0 to 1. So it'll be 1/2 of, let's see, 1/2 of tan inverse of 1 minus 1/2 of tan inverse of 0. So let's see, tan inverse of 1, that would be first quadrant here, rise over run would be the same thing. This is a 45-degree angle, or pi over 4. So that's 1/2 of pi over 4. Minus 1/2 of opposite over adjacent would be 0. So on the unit circle, that's just flatlining. So that's at 0 degrees or 0 radians. Oh, and you can use a calculator for this stuff anyway. So then we get 1/2 of pi over 4, which is pi over 8. Now, if you have gotten to the point where you've memorized that the integral of 1 over x squared plus 1 dx is tan inverse, then go ahead and jump straight to that step, or not to that step, I guess, but to this step. And that one comes up enough in this course where maybe that's worth memorizing. Otherwise, you got to go through this trig identity or trig substitution thing every time. Okay, I want to do one other example that refreshes you on u substitutions. Maybe I should have done the u sub first, but whatever. All right. So in this one, we'll do the integral from 0 to 1 of 6t squared over 3 plus t cubed dt. Now, the u substitution, typically the thing you're looking for is what can you set equal to u? And then when you do du, kind of you take the derivative, whatever you're left with eats up like almost everything else in the problem. So in this case, it's typically the bigger the power, the more likely you are to choose that, unless it's a substitution, unless it's a trig thing. So in this case, we're going to let u equal 3 plus t cubed. And then if we do du or du dt and then multiply the dt over, we're going to get 3t squared dt. Okay, so there's our u substitution that we're doing. So then if I go back to this problem, I'm doing the integral from 0 to 1, except I'm not really working in terms of t anymore. I'm working in terms of u. So it's really u of 0 to u of 1, where these are t values, the 0 and 1. And you could, if you want to, plug in 0 and 1 here and get those actual values. And so I've got 6t squared on top. I've got a u on the bottom. And then I'll just leave this here for now so you can see what happens. 6t squared dt. But dt is really du over 3t squared. And then the nice thing about this is that the t squareds will cancel. The 6 over 3 turns into a 2. And I've got the integral from u of 0 to u of 1 of 2 du over u. So you might remember, if you want to, you can factor out the 2. And you've got 1 over u du. It's from u of 0 to u of 1. So that's going to be, you might remember, since the derivative of ln is 1 over u, the integral of 1 over u is the ln of absolute value of u, if you recall that one. And here, we'll just keep this in terms of u. So if I plug in 0, it's 3 plus 0 cubed is 3. If I plug in 1, 3 plus 1 cubed is 4. So I'm going from 3 to 4. So this is going to be 2 ln of absolute value of 4 minus 2 ln absolute value of 3, which ends up being, I don't know, 2 ln. Actually, I can get rid of the absolute values. I can factor out a 2. I think you might remember the property that ln of a minus ln of b turns into ln of a over b. You could even bring that 2 up and then square the 4/3 if you wanted to. But at this point, I think that's totally fine, leaving it like this. I'd accept this answer. I'd take this answer. I'd probably even take that answer. And odds are I'd ask you to turn it into a decimal and round to 3 places anyway. So, okay. So that's example 2. I'm not doing any other examples, but just so you remember, we did derive in the last class the formula for arc length. And so that's the integral from t equals a to t equals b. By the way, this is like you've got some curve going on here. This is r of t. And we're looking from t equals a to t equals b, let's say. So we're looking for how long this arc is. And we figured out in class that if r of t is 3-dimensional, then you really are just doing this thing here, dx dt squared plus dy over dt squared plus dz dt squared dt on the outside. That's in 3D. If it's 2D, you would just get rid of the z term. Remember, r of t here would be x of t, y of t, z of t. And if you prefer, you could think of this whole thing, a to b, as the norm of r prime of t squared. Oh no, it's square rooted, so it's just r prime of t dt. Now, if you don't quite see this notation, just work this out a little bit, and it's pretty quick to get that. So either one is fine with me. Typically, you're going to almost immediately turn this into that anyway, but it's up to you how you want to memorize it. So one other thing, I think the term parametric functions comes up, or parametric equations. Just remember, if you have r of t equals, like, I'm just going to make this up, like 3 cos t, 2 sine t plus 4, and negative t, then your parametric functions are just x of t equals 3 cos t, y of t equals 2 sine t plus 4, and z of t equals negative t. That's the parametric form. So this is vector form. This is parametric form. They're really practically the same thing. But I think the term parametric form shows up a few times on the homework. So, okay, I will hope to see you guys soon, and take care. I love you all. Peace.